Hello, Calculus 1. Welcome to episode 8 of Math 141, Summer 2020. Today we're going to be talking about summer sine over cosine lines. The joke, do you get the joke here? The joke is that these are summer tangent lines, summer tan lines. Tan lines, get it? Get it? Tan lines. If you want to be really cool and really popular and really funny, what you should do the next time you're at a party is you should write sine over cosine on your hand or your arm. I guess your arm would probably make more sense. And then go up to your friend and be like, man, I got these really bad tan lines. Take a look. And then bam, you roll up your sleeve or whatever, wherever you've written wherever you've written sine over cosine over and over again. And boom, tan line. Instantly going to make you the most popular person in school, no doubt. See, we talk about a lot more than just math here. Great life hack there. Anyways, in all seriousness, the two sections from which we're going to do some problems today are 3.4, the derivative as a rate of change. So we've kind of talked about this a little bit to this point, how we can interpret the derivative of a function as a rate of change of that function. And in particular, we will look at the relationship between velocity, position, acceleration, and so on, and how they are all related via the derivative. And then in 3.5, we learn the derivatives of our favorite trigonometric functions. So really, once you know sine and cosine's derivatives, from there you can use the product rule and the quotient rule to help you derive the other derivatives of secant, cosecant, tangent, and cotangent. So, like we've seen before, everything really breaks down to sine and cosine, and derivatives are no different. Before we get into that, I wanted to issue a public apology for, in my last video, I realized just this afternoon actually, that you have not yet learned the chain rule. So, but that was something which I used a couple of times in the last video. So I am sorry for using the chain rule before you've been introduced to it, for using the chain rule before you were introduced to it. I got a little bit excited, a little bit ahead of myself. It's a very fascinating and fun little rule which we're going to learn about in section 3.6. So ultimately it is something which you're going to have to know. And it is going to make your life easier, I think, in some cases. In other cases, probably a little bit harder. But in any case, I do apologize. All of those problems from the last time you could have done without the chain rule. But I mistakenly thought that you had already covered it. So anyways, I apologize again. I can't wait for the next video in which I will get to legally use the chain rule as much as I desire. Wahahaha. So now that that is over with, let us finally get into some problems. I have 8 of them picked out for today. It's relatively short homework assignment. So I'm going to do, this is going to be almost half of the problems, but that's okay. So let's go ahead and get started. The first problem which I want to do is problem 3. This problem has a whole bunch of parts. So let's get started here. A rock thrown vertically upward. I hate whenever it does that. Thrown vertically upwards. Vertically upward. From the surface of the moon. Oh, I didn't read that part of the problem the first time. That's exciting. The surface of the moon. Heck yeah. I guess that makes more sense given the problem which we're about to do. At a velocity of 8 meters per second, reaches a height of, and this is going to be the key information here. Why don't I go ahead and write that in a different color actually? Let's use our technology here. A height of s equals 8t minus 0.8t squared meters in t seconds. meters in t seconds. So for example, if I wanted to find out how far up it was, how high it was after 1 second, I would plug in t equals 1, and I would get 7.2 meters. Okay. So that is our problem. As I said, there are several parts to this. So we'll go step by step here. Some of them maybe we won't go through all of the work. We'll see. Simply because there are so many parts, and obviously I want to be efficient with time. The first part says to find the rock's velocity and acceleration at time t. Okay, so we want velocity and we want acceleration. So that brings us to this relationship between velocity and acceleration, which I mentioned at the beginning of the video. So in this case, s is our height function, right? So let me go ahead and, so s here, s of t equals our height. So what that means, well, velocity is going to be the derivative of height, right? Velocity is change in position, really. Velocity really is change in position. It could be height, as in this case. It could be like if I'm driving somewhere, for example, miles per hour, that's velocity, right? Over change in time. So change in position, in this case, again, height. Okay, so that's what velocity is. So it's going to be the derivative of the height. And the second derivative of that is going to be the acceleration. Okay, so that's going to be change in velocity over time. Velocity over change in time. Okay, so what you notice is that so height here, whenever we take the derivative of height, we're looking at change in height, right? Position, which in this case is height. Change in height over change in time. Then, whenever we look at the derivative of velocity, when we take the derivative of s prime, we are looking at change in velocity over change in time. So if we took a third derivative, that would give us change in acceleration over change in time. Okay, and in fact, we have a word for that, which is jerk. We'll get to a problem involving jerk a little bit later, so I won't write it out here. But as you can see, this is how we get the notion of the derivative as a rate of change, Okay, so those are the formulas that we need. So let's go ahead and compute these things. So let's first compute s prime of t. Well, we have s of t. Let me go ahead and copy it down here just so that we're not constantly going back up. So let me copy that, I'll put it in black. So s of t is 8t minus 0.8t squared. Okay. So s prime of t then, put that in blue, s prime of t is going to be, okay, well, remember, since the derivative is additive, I can just take the derivative of 8t. So that derivative is just 8, right? This is 8t to the first, so we can just apply power rule. Oh, you're going to sick of me saying power rule again, I know. And then the second derivative, so now we can subtract the derivative of 0.8t squared. Well, I'm going to bring that 2 from the exponent down front. So I've got a 2. I still have this constant 0.8, right? The constant we can just leave there. And now I've got a t to the first power because I lowered the exponent by 1. So this is really just 8, oops, I don't know what that was. 8 minus 2 times 0.8 is going to be 1.6t. And so this is our velocity. Okay, so that's our function for velocity. 8 minus 1.6t. So now acceleration, we're just going to take another derivative of s. So we're going to take the derivative of 8 minus, or this guy rather, the derivative of 8 minus 1.6t. Well, the derivative of 8, that's just 0. So I'll go ahead and write that here so you see where it goes, but it's just 0. And then the derivative of 1.6t, well, that's just 1.6, again, by the power rule. And so s double prime of t is just negative 1.6. Okay. In this case, there is no t anymore. So we see the acceleration is constant. Let me write acceleration and put that in the box. Right, the acceleration, since it doesn't have a t in the formula, it doesn't depend upon time at all. And so the acceleration is constant. Okay, very nice. Now we are going to look at part B. So part B says, how long does it take the rock to reach its highest point? The rock to reach its highest point. And for this, I think it might be helpful to draw a picture. Okay, so I'm not gonna, I'm not the best at drawing pictures, and this isn't gonna be a super detailed picture, but I wanna at least sketch the general shape here so that we have an idea of what's going on. So if I were to graph the function 8t, go ahead and write it again down here. So s of t equals 8t minus 0.8t squared. So this is the height, remember? So this is the height function. Okay, so let me look. If I were to look at this on a graph, okay, let me see. So this is going to be a parabola. It's going to open downward. Is that right? Let me see. So let's plug in a few points here. I know this is going to be a parabola, but let's plug in a few points to find out exactly what it looks like. So if I plug in, let me plug in time and height to get a sense of the shape here. Okay, so let me see. It looks like when t is 0, okay, so if I plug in t equals 0, then I'm going to get 8t minus, so that's going to give me 8 times 0 minus, okay, so that's just 0, 0. Okay, so that's just the origin there. Okay, I'm going to just stick to one color here. So now if t is 1, so after 1 second, it's going to be 8 minus 0.8 times 1, so that's going to be 7.2. Okay, so this is going to be like 1, 7.2, I don't know, maybe it's up here. 1, 7.2. Okay, so now actually let me write that to the side because it might get in the way here. So we'll just leave it over here in the graph, in the table. If I plug in a 2, let me see, so then that's going to be 16 minus 0.8 times 4, that's 16 minus 3.2, that's 12.8. Okay, so it looks like 12.8, so that's going to be somewhere over here-ish. So the point is that our graph, I don't know exactly what it's going to look like, but I do know that it's a parabola. It's going to open downward because of this negative, right? That negative sign means it's going to open down. And we can actually kind of see that shape here. So our parabola is going to look something like, this is just be a rough sketch, but something like this. It's going to go through these points, okay? And I don't know exactly where its maximum height is. In fact, we're going to have to find that here. And then it's going to keep on going down this way. So its maximum height is going to be up here, right? It's going to be like at this point. And if I look at the tangent here, well, I can see to the left of this, so here, the derivative is positive, right, on this part on the left, because it is going up. On the right here, the derivative is negative. So derivative, because remember, derivative is like the slope, derivative negative here. So the highest point is going to be at this point, and that's where the slope is at 0. It's in between this positive part and this negative part. So it's at its highest point when the derivative, so that would be s prime of t, equals 0. Okay? Okay. So we have a nice formula for s prime of t. We found that s prime of t is equal to 8 minus 1.6t minus 1.6t. And so we want s prime of t equals 0. So then we're going to set 0 equals 8 minus 1.6t. Okay, so then this is the same as 1.6t equals 8. And that is the same as t equals 5. And so t equals 5 is when it's at its highest point. At highest point. Highest point. In general, this problem demonstrates a very important principle, and that is that the highest point, the maximum point of this function, or of any function, or the minimum point of a function is generally going to be given whenever the slope is 0, or sometimes on the endpoint of a particular interval. I believe that's something we'll talk more about later in the course. So I'm not going to dive super deep into it now, but I hope that you can see, at least in this case, why the highest point is going to be whenever the derivative is 0. Again, if we look at the shape of this graph, we can see roughly it's going to be a parabola opening downward. On the left part, the derivative, it's increasing, right? So for example, this point here, which I'm going to draw, that point is not the highest point because the derivative is positive, so it's going to keep on getting higher, right? It's going to keep on increasing. This point over here on the right-hand side also certainly is not the highest point because the slope is negative, meaning that a point just to the left of it is going to be higher. So the only place where we can possibly be at the maximum is whenever the slope is 0. Okay. So that gets us through part B. Part C now is going to be very simple because in part B, we basically did all the hard work. Part C now asks, how high does the rock go? Okay. So how high does the rock go? Well, the rock is at its highest point at t equals 5. So all that we need to do is plug t equals 5 into the height formula. Because we know t equals 5 is whenever it's at its highest point, so we just plug that into the formula for the height to find out what is the height at 5 seconds. Let me see, that gives us s of 5. Okay, so s was 8t minus 0.8t squared. So that's 8 times 5 minus 0.85 squared. Let me see, that's 40 minus 0.8 times 25. Okay, well, let me think about this for a second. 0.8, that just means 4/5. 1/5 of 25 is 5, so 4/5 is 20. So this is just 40 minus 20, and that is just 20. So really, I guess I should say 20 meters. And really, I guess in this problem, I should say t equals 5 seconds, but you get the idea. Okay, so like I said, we pretty much did all the hard work in part B, In part B, we found the time at which the rock reaches its highest point. So then to find how high the rock went, all that we had to do was plug in that time into the formula for the height. Let's jump to part D. I'm thinking part D and E, I'll probably just mention how you would do them. And then I will I will leave them to you to actually to put the finishing touches on them. So part D asks, how long does it take? Actually, you know what? Let's go ahead and do it, because some of these later problems I don't think are going to take too long. To reach half its maximum height, how long does it take to reach half its maximum height? Okay. So what we want then, we want to find a t, we want to find a time t such that s of t, remember s of t is the height, so this is height, equals half of 20 meters, right? Because 20 meters was its maximum height. So half its maximum height, this is just 10 meters. So we want to find a t such that s of t equals 10. Okay, well, we have a nice formula for s of t. So that just means that 10 equals 8t minus 0.8t squared. I don't know about you, but I'm feeling 22. No, but I don't like this 0.8 business going on here. Ew, yucky, right? So what I'm going to do, well, actually, let me go ahead. Yeah, let's go ahead and to get rid of that 0.8, again, 0.8 equals, 0.8 is just 4/5. So if I multiply both sides of this by 5, I can do that, right? I can multiply both sides of an equation by the same thing. Then I get 50 equals 40t minus, and 0.8, so that becomes 4t squared. And from here, it just becomes, I should have written that line in blue, but that's okay. So from here, all that we need to do is, this is just quadratic, so 4t squared minus 40t minus 50 equals 0. Oh boy, can I do this? Come on, Bailey, you can do it. 2t, come on, let me think. Let me see, can I plug in 25 and 2? No, that won't work. Can I plug in 5 and 10? Oh, I think I can, if I do 5, let me see. No, but I think 5 and 10 will give me 10 and then a 20. Yes, that won't work. 5. Is that it? Are those the only two ways I can factor this? Oh, but what I can do, maybe instead of 2t, maybe I want 4t and t. I think this will work. And now if I plug in 25 and 2, I don't think will work. 2, 25, no. What if I do 5 and 10 now? I bet I can make it work. If I do a 10 here, if I do 5, no. Well, worst case scenario, we have the quadratic formula. So we can just solve using the quadratic formula. Maybe we could have factored it. I don't think that we could have. Oh, now let me go ahead actually and divide everything by 2. It'll make my life a little bit easier, I suppose. So then I can get 2t squared minus 20t minus 25 equals 0. Let me try one more time. 2t, t equals 0. Let's see, so if I do 5 and 5, then I'm going to get a 10 and a 5. Yeah, that's not going to work. And then if I do If I do 25 and 1, that was one possibility I didn't do last time. But that's not going to work. Yeah, so we'll just use the good old quadratic formula. And that is, let me see, negative b. This is how I learned it. Negative b plus or minus the square root, of b squared. B squared in this case is going to be 400. B squared minus 4, 8 minus 4 AC, negative 25. All over 2a. I can factor things this way. I don't wanna, but I wanna get an A. That's how I learned it. So negative b plus or minus square root of b squared minus 4ac all over 2a. I can factor things this way. I don't wanna, but I wanna get an A. Okay, good. So let me go ahead and work through this. 20 plus or minus square root. Now I'm curious. 400 minus, well, really it's going to be a plus, so that's going to be plus 200 all over 4. Yeah, and this is going to be ugly because this is going to be the square root of 600. So I'm going to leave it to you to solve from here. Now, I guess I should point out, you will get two solutions. You will get two solutions, right? You'll get one from, so you get 20, I'm just going to write it, fine, 20 plus the square root of 600 over 2. And you can simplify that, but I'll just leave it over 4. And 20 minus the square root of 600 over 4. Right, because of this plus minus here. Now, if we go back and look at our graph, that makes sense because we're at half of the height, say at this point here maybe, and at this point here, right? One on both sides. One on both sides of the maximum height here. So the question here is asking, how long does it take the rock to reach half its maximum height? I would interpret that to mean we want the smaller one because we want to know how fast, we want to know the quickest, the shortest amount of time that it took it to get to that height. So we want the smaller answer. Okay. So this is one of those times where you need to take the problem and the context into account. And we're going to want the smaller answer out of these two. Okay. But that will then be our answer. Okay. Finally, we look at part E. Part E asks, how long is the rock aloft? Is the rock aloft? Well, now we want to solve 0. We want to solve S of t equals 0, right? Because we want to know when has the rock landed again, right? Now again, so S of t, this time I promise I'm not going to go through the full thing. Remember, so really what we're solving here is 0 equals 8t minus 0.8t squared. Again, we will get two solutions. We actually know one of the solutions, t equals 0, and something else. Okay, again, if we go back up to our picture, we can see that, again, at some point right around here, we'll cross the x-axis again. And that is the point at which the height is 0 again. So, how long is the rock aloft? Well, our answer will be the second one, the second time, not t equals 0, because that's just when it starts. Our answer will be the bigger one. Oh, and wouldn't you know it, it is pouring again here in Colombia. Oh wait, that's just that's just the AC coming on in this room. I apologize. I thought it was rain again. Today's been storming, absolutely pouring off and on again, so. Okay. Alrighty, so that does it for problem 3. Wow, that one was a doozy. I promise they will not all be that long. In fact, like I said, some of the ones at the end I anticipate being quite short, so that's why I felt okay spending a ton of time on that one. Problem 4 now, this one is going to involve a picture, which I will do my best to portray below. So the accompanying figure shows the velocity, and that's important. The velocity f of v equals f of t. V, not the word equals, silly goose, equals f of t of a particle moving along a coordinate line. Moving on a coordinate line. Okay, so I'm going to do my best here to make this picture helpful. Well, let me start all the way at the left to give myself as much space as possible. Okay, and I'll draw my axis there. Okay, so this is t here. This is time. So that's t for time. And then up here, this is v, or velocity. Okay, so let me sketch this picture here. First, it goes up a little bit, and I will clearly label every single point. So this point here is the point 1, 4. After that, it goes down to say here. Okay, so this point where it crosses the axis, this point is 2, 0. And now this point down here, this is 3, looks like we're at -4 now. Okay, then we're gonna go over a little bit. So I'm still at -4 height, but now I'm at 4, -4. And now I'm gonna shoot back up again, up to where my height is 4. So same height as this first point. And so this one here is 6, 4. This is 6, 4. And then we're gonna shoot down to the x-axis again, to the point 8, 0. That should be 8, 0. And then it just continues on along the axis here. It looks like it goes until this end point here is 10. So this is 10, 0. And then of course we have the origin, not 10, that one's not 10, 0. This one is 0, 0. Okay, so I hope that I have drawn this well enough for you. Again, this is velocity, is what this is a graph of. Okay. So then there are a few questions. The first question asks, when does the particle move forward? When does the particle move forward? It also wants to know, when does it move backward? Question mark, backward? When does it speed up? Question mark. Speed up? Question mark. Slow down? That's a lot of questions all in one question. Okay, so when does the particle move forward? Let's first address this. So the particle moves forward. Well, what does that correspond to? That means that the velocity is positive. Okay, and then similarly, moving backward is whenever the velocity is negative. I'll make a note, it doesn't ask for it here, although it'll probably, let me see. Yeah, it does, okay, it sort of asks this later. So then it's standing still whenever velocity is 0. Okay, so it's moving forward if the velocity is positive, backward if the velocity is negative, and it is still if the velocity is 0. Okay? So that's how velocity plays into this. So if we look at the graph, again, the graph is showing us velocity. So the first part, when does it move forward? This is just asking, when is the velocity positive? And we can look at this picture and say, okay, well, the velocity is positive. It looks like from t equals 0 up until t equals 2, right? We can see along this portion that the graph is moving forward because velocity is positive. And again, over here, the velocity is positive. So it looks like, type an equation. Okay, so it wants the answer in terms of an equation or inequality. So in this case, it looks like it is positive whenever t is between 0 and 2, right? It's not moving forward at t equals 2, because at t equals 2, the velocity is 0, so it's not moving forward. It's very instantly standing still for just a brief, and infinitesimally small moment. Or, well, I guess I'll say and. Whenever t is similarly between, oh, I forgot to label this point, I'm sorry. This point here is 5, 0. Yeah. So, and whenever t is between 5 and 8. Okay. When is the velocity negative? Well, that is just whenever the graph is negative, and as we can see, that is for t now bigger than 2 and smaller than 5. Okay, again, if you look at this graph, the only time the graph is negative is from t equals 2 to t equals 5. So when does it speed up? That's the next part. So it speeds up. Well, this is, so when, in other words, this is just asking, when is velocity increasing? So we're asking, when is this graph increasing, right? When is this graph increasing? And that is the same thing as asking, when is the slope positive, right? The graph is increasing whenever the slope is positive. That's what positive slope means. And similarly, slow down. Well, this is just asking, when is slope negative? For the same reason. Okay. So the slope is positive, it looks like, from, let me see, from 0 to 1. Okay, so t 0 less than t less than 1. It is also positive from 4 to 6. So 4 less than t less than 6. And I think that's everything. Yep, those are the intervals over which the velocity is positive. So then where is the slope negative? It looks like from 1 to 3 and from 6 to 8. Okay, so 1 less than t less than 3, 6 less than t less than 8. Okay, very good, very good. I should notice, so when does it speed up? This is also asking, when is velocity increasing, i.e., when is acceleration positive? Because remember, acceleration is just the derivative of velocity. Oh, and in fact, that leads me right into part B of this problem. I didn't even mean to do that, but part B, when is the particle's acceleration positive? Acceleration positive. When is it negative? And when is it 0? Well, let me remind you, pretty much like what I just said, acceleration is the slope of velocity. Okay? So I'm going to leave it to you there. Yeah, I'm going to leave it to you there to find those points. It pretty much is going to be what we just did in part A. Part C, when does the particle move at its greatest speed? Move at its greatest speed. And there, okay, so you have to be careful with this one because speed is the absolute value of velocity. Okay, speed is the absolute value of velocity. So what that means is that we're not just looking for whenever velocity is the highest, we're looking for the absolute value of velocity is the highest. So when is absolute velocity highest? Well, if we look at our graph, the absolute value of velocity, so it clearly here is 4, right? So the height of the graph here is at 4. We can see this is the highest point. But also down here, we see that the velocity is -4, so the absolute value of velocity down here is still 4. So the speed here is 4 as well. So it looks like our answer is going to be, and I'll leave it to you to write out the formal intervals, but it's going to be at these points, these 2 points, and then over this interval down here. Okay? And finally, part D asks, when does the particle stand still? Stand still for more than an instant. Well, I think we mentioned this in part A. Standing still, well, that just means velocity equals 0. So this is literally just asking, where on the graph is the graph going to be along the x-axis for more than just an instant? Right? We notice here and here at these 2 points, technically the velocity is 0 at those 2 points, but it's just 1 point. So that's what it means whenever it says an instant. Here, it's just standing still for an instant. But over here, from this 8 to 10 region, over this interval, we can see that it's truly standing still for more than just a split second. So this is the interval over which they're interested in, this 8 to 10 second region. Okay? All right, so I hope that helps help you see the relationships between, again, velocity, position, acceleration, and speed. Let us now jump to some trigonometric problems. These problems I think we're going to go by a little bit more quickly. So problem 9 asks us to find dy dx. These are more my types of problems. I like these. These are very, very much just pure abstractness, which is what I personally like. They're more abstract. I like stuff that looks more like equations and pictures personally. So I'm excited to do these. I hope that you are excited as well. So the first one tells us to find this derivative. Our function is y equals 1 over cosine plus 5 over tangent. Now we could use quotient rule. Right, I've got two fractions here. But I think it's easier to notice, well, 1 over cosine x, actually I'll write it up here. 1 over cosine x, this is just secant x. And 5 over tangent x, well, this is just 5 arctan x. No, excuse me, not arctan, cotan. So this right here is 5 cotangent x, right? This is 1 over tangent. 5 times 1 over tangent, which is cotangent. Now, these are derivatives. I hate memorizing things, but I think that you're probably best off memorizing these secant, cotangent derivatives, all of those. You can, like I said at the beginning of this video, you can derive them using product rule and quotient rule. In fact, I think mostly quotient rule. However, it's probably easiest just to memorize these, and they're going to come up enough that it would probably be worth the time to do so. So dy dx then is going to be the derivative of secant. The derivative of secant is secant tangent plus 5 times the derivative of cotangent. So that's just 5 times negative cosecant squared of x. And so you can bring that negative out and just write this as minus 5 cosecant squared. But I'll go ahead and leave it here. Okay, so the key observation here was that rather than using the quotient rule, so we could do that if you want to, but it's quicker to recognize these trig identities. That 1 over cosine, well, that's just secant. And 1 over tangent, that's just cotangent. Okay, so that could save you a little bit of time in this case. Okay. All right. Let us continue. Yeah. To problem 10 is the next one that I was hoping to do. See, I told you these would go by a little bit more quickly. Problem 10 says find, this one's very similar in the setup, but it's actually going to work out quite differently, and you're going to have to be a little bit creative here. For the following function, so the function is y equals x squared times sine of x times cosine of x. Okay. So here's the thing. We know how to use product rule. We know product rule, right? We know that f of x, g of x, if I want to take the derivative of all of that, that becomes g of x times f prime of x plus g prime of x times f of x. But the problem here is that it kind of looks like I have 3 functions, right? I've got x squared is a function, sine of x is a function, and cosine of x is a function. But what I can do is I can group 2 of them together. So for example, so what I'm going to do is I'm going to give these guys names, and I'm going to say, I don't know which ones I want to group together, but it doesn't matter. I'll just say let x squared, or let f of x equal x squared, and g of x, and this is the trick, be sine of x times cosine of x. I can do that. right? So what I'm doing is I'm writing these two functions, sine of x, cosine x. I'm writing that as one function. This now allows me to use product rule because I have the product of two functions, f of x and g of x. So dy dx is going to, again, I'll just write it here and then we'll plug in our stuff. F g of x times f prime of x plus g prime of x times f of x. So let's go ahead and calculate us some derivatives. Well, g of x, okay, so that's just sine of x, cosine of x. F prime of x, okay, so this is g of x. F prime of x, so the derivative of x squared. This is a very straightforward power rule situation. So this is going to just be 2x, so 2x, that is f prime. Okay, that's power rule again. So now plus, okay, g prime, this is where we're going to have to be, I'm going to step aside to calculate g prime actually, because g prime is a bit uglier. So g prime, because to calculate g prime of x, I'm again going to have to use product rule. Right, so g prime of x is going to be, the derivative of, is going to be sine x times the derivative of cosine of x, right? Sine of x times the derivative of cosine plus the derivative of sine, I don't know why I put a second brace there, derivative of sine times cosine, right? This is just product rule now applied to this function g of x. So g prime, okay, well let's see, so that's sine of x. Okay, the derivative of cosine, that's going to be negative sine of x, right? And then plus, okay, derivative, so let me see. So derivative of sine is going to be cosine of x. Okay, again, those are two very important identities which come from this section, which you'll want to familiarize yourself with, those two derivatives. And so this comes out to cosine squared minus sine squared. And actually that is just cosine of 2x, right? So g prime of x we just found to be cosine of 2x, so plus cosine 2x, and then f of x is just x squared. And so again, you could simplify this if you wanted to, and I encourage you to do so. It will make it easier to enter in my math lab, but in terms of the actual work, we know how to use product rule on two functions, so we can group two of our functions together, and then from there, we have to use product rule within a product rule to give us our solution. Again, the derivative of sine is cosine, and the derivative of cosine is negative sine. Okay, we get that negative introduced there. But other than that, it's not so bad. Okay, and actually, as I look at the solutions on my math lab, rather, it looks like they don't make this substitution. So actually, they don't make this substitution at the end here, the cosine 2x part. They just leave it as cosine squared minus sine squared. Let me put a star there. So you probably actually want to just leave it in that form and substitute that in up here instead. But other than that, it works out exactly the same. Okay, we just went above and beyond because that's what we do as South Carolina Gamecocks. We go above and beyond. Forever to the hashtag Spurs the F up. Okay, problem 12 now. Let's see here. Problem 12. Oh my goodness. By computing, this is actually a really cute problem. I really like this. The first few derivatives. and looking for a pattern. Find, get ready for it, brace yourself, the 990th derivative. Yes, you read that right, folks. The 990th derivative. What the heck? Sine of x. All right, well, this video, it turns out it's going to be a little bit over an hour as I sit here and calculate 990 derivatives for you. No, actually, no. So let's look for patterns, as it suggests, and I bet you we can be a bit more clever than that. Look for patterns. The way that I recommend going about this, and you don't have to do it this way, but this is how I like to look for patterns. I like to make myself a little table. So in the left-hand column, I'll put n, and in the right-hand column, I'll put the nth derivative of sine of x. Okay. So for example, whenever I plug in n equals 1, this just means take the first derivative. So I'll write it out this time. D dx of sine of x. Well, that's cosine of x, like we just said. Okay, so now for n equals 2, I'm just going to take what I'm going to do is I'm just going to keep on taking derivatives. So then the derivative of cosine is negative sine of x. The derivative of negative sine, okay, well, the derivative of sine is cosine. Let me see, and then I've got a negative, so this is going to be negative cosine of x. Okay, and then the fourth derivative, well, let me see, the derivative of cosine is negative sine, and then I have a negative out front, so I have to negate the negative, and I'm back to sine. Okay, and now the derivative of sine is cosine. And wait a minute, would you look at this? Now we're going to get ourselves a pattern, right? So we've got the first derivative is cosine. The second derivative is negative sine. Then we get negative cosine. And then we're back to sine. And then after that, it's just going to restart, right? You see I've got cosine here as the first derivative. And that's also the fifth derivative. So we can see it's also going to be, if we add another 4, it's going to be the 9th derivative, the 13th derivative, and so on. And so, what we have to ask ourselves, so if I look at 990 so we have to look at 990 divided by 4, because that gives us, because our pattern has length 4, right? In other words, it repeats itself every 4. So if I do 990 over 4, or I'm going to do this in my head, 250, that's going to be 247. But then I'm going to have 2 left over. The great thing about a YouTube video is that I don't have to, I can just do that quickly, because you can pause it and work through it as you need to. Okay, so what this means, well, every multiple of 4 is going to be sine of x, right? So in other words, I can write this as, how do I want to write this? Yeah, so after I take, how do I want to say this? So this means that after the first, so what does okay, let me just write it. 247 times 4 plus 2 equals 990. Yeah. All right, if I multiply both sides of this thing up here by 4, that gives me this thing. So this means, in other words, 988 plus 2 equals 990. Well, from our pattern, we see that every fourth derivative, right, and 988 is divisible by 4. So every fourth derivative is sine of x, right? We saw that the fourth derivative here was sine of x. If we then jumped up another 4, we would be at 8, and we'd be at sine of x, then 12, and so on. So that means that the 988th derivative of sine of x is sine of x. So then we just need to take 2 derivatives of sine, right? Because our first derivative will get us to 989. Take 2 more derivatives. And we see that the 990th derivative of sine of x, well, we've already taken some derivatives up here. And indeed, so when we take the first derivative, we get cosine, and when we take the second derivative, we get negative sine. So we take 988 derivatives, and after that, we're back at sine. And then we take 2 more to get to 990, and that gives us our negative sine. So an important takeaway from this is we can see that the derivative of sine is cyclic. It has this pattern where it repeats itself. Where it repeats itself. Cosine behaves the same way, right? Because cosine, if we look at those derivatives, derivative of cosine is negative sine. And then if we took a second derivative of cosine, then we would get negative cosine. If we do a third derivative, then I'm going to get positive sine. And then if I do a fourth, then I get cosine back. And it's going to cycle back again now. Okay? So cosine is similar. I pose the question to you. Our tangent and the other trig functions like that as well. I encourage you to check it out. The cyclic nature of these derivatives can be very important sometimes. In calculus 2, it comes up a lot, and it becomes very important whenever we do something called integration by parts. So it's important. It's an important observation, and I encourage you to play around with it. Problem 13, I think I'm going to skip in the interest of time. It's very similar to one which we did earlier. The one piece of this which we didn't talk about, I'll talk about very quickly here. So position, so I'll say if position, which again, maybe it's height, maybe it's distance, whatever. If position is the function, we'll call it f of t, then, well, let's go ahead and look at what each of the derivatives is. So f prime of t is the velocity. We talked about that before. We briefly mentioned this. The absolute value of f prime of t is speed, right? The second derivative is acceleration. And then the new part, which you need for this problem, which I haven't talked about yet, it's the reason that I awkwardly wrote the word jerk a moment ago, is jerk. The third derivative, or change in acceleration over change in time. So I'll write change in acceleration, that's a delta. Change in acceleration over change in time is jerk. Okay? So whenever someone's being mean to you, just tell them that they're being a change in acceleration over change in time. That'll totally own them. And you'll win that battle for sure. Okay, problem 16 is next up. And this one looks really scary, which is why I wanted to do it, because it looks really scary, but it's actually not so bad. So here our function is y equals 3 times cosecant x plus cotangent x, and then cosecant x minus cotangent x. So when we first look at this, my first instinct is like, I gotta do product rule, because I've got these two things being multiplied together. I've got this quantity being multiplied by this quantity, and quantities being multiplied, well, that's a product, and that means do product rule. But let's go ahead and multiply it out. Sometimes multiplying things out actually makes your life a little bit easier. So I've got this 3 here. Well, notice I've got these two are conjugates of each other, right? I've got like a plus b times a minus b, right? Where a is cosecant and b is cotangent. So this really just becomes, when I multiply a plus b times a minus b, I get a squared minus b squared. So that just becomes 3 times cosecant squared minus cotangent squared. And if you know your trig identities, now you are so very excited, because guess what cosecant minus cotangent squared is? This is just a big fat 0. Excuse me, not a big fat, that's a 1. That's what I meant to say. I was getting a step ahead of myself. I was a step ahead of myself because now this is just y equals 3, and the derivative of a constant is just 0. That's where the big fat 0 comes in. So this horrible looking mess at the beginning, you were actually able to turn into something very simple. This is by doing a bit of multiplication. And again, this is why it is so important that you know your trig identities. Okay, they make your life so much easier. So I encourage you to take the time and get to know them. Okay, the final problem that I want to do, let me see, is problem 19. Oh, this one's also a cutie. This one also looks big, bad, and scary, but it's not. 19, so find, oh, they changed up the variables on us. Whoa, hold on there. dp dq. Okay, this is the same thing as dy dx, they just changed the variable. For p equals cosine of q minus sine of q over cosine of q. And oh geez, oh my goodness, again, my first thought, not product rule this time, but this time I'm thinking, oh man, I gotta do the quotient rule, which is even worse than product rule in my opinion. It's even more tricky. Right, I've got a quotient of things. I'm gonna have to do quotient rule with trig. Yummy, so fun. But check this baby out. So in general, a minus b over c, I can split that up as a over c minus b over c, right? So how can I rewrite this? Actually, you know what? I'm gonna leave it to you. But this is the key here. This is the key. Instead of trying to differentiate this whole fraction, break it up into 2 fractions like this. And then from there, you can use trig, well, the first fraction, from there, one of your fractions will be very nice and easy to work with. And then the other fraction, you can rewrite using trigonometry. And then from there, it's just a derivative that you know, or one of the ones that you learn in this section in which you should commit to memory. So I think from here, you guys are going to be all set. I should also mention that if you do use quotient rule, you will get the same thing. If we had used product rule in this problem, it will all work out the same. So it's not wrong to do those things. But I think that you would agree that it's certainly worth, it's probably a nicer idea to try and figure out these little tricks that you can do. That does it for this video. please send me some stuff that you want to see me do in future videos. I hope that everybody had a good long weekend, and I will see you in my next video where we will finally learn the chain rule, which I can then legally perform in front of you. So super excited about chain rule, and I hope that you're excited too. Take care.